Today, we'll be taking on a problem from the 2018 Australian Mathematical Olympiad. Unfortunately, I can't find out a whole lot of information about this competition, but suffice to say, it's used to select the Australian participants in the International Mathematical Olympiad. Today, we're taking on problem 5 from the 2018 AMO. This gives us a pretty simple recursive sequence and asks us to prove that the 2018th term of the sequence is divisible by 2018 squared. My coffee's ready.
Coffee Time Math with your host, Wrath of Math.
All I want for Christmas is to solve this problem with you. Let's do it. Alright, so what have we got going on today? Well, we've got an infinite sequence whose terms we will call A1, A2, and so on. It's a recursive sequence defined like this. The first term, A1, is equal to 1, and for n greater than or equal to 2, an is the sum of the previous terms multiplied by the position of the nth term in the sequence, which of course is n. So an is equal to a1 plus a2 all the way up to plus an minus 1, all multiplied by n. We want to prove that 2018 squared divides the 2018th term of the sequence. So we want to prove a 2018 has at least two factors of 2018 in it. Now, as you might suspect, as I would certainly suspect based on my experience with these math competition problems, is when they try to be cute and introduce the year of the competition into the problem, there's not really anything special about that specific number. And in fact, there's a more general property that we're really trying to weed out. So what would the more general property related to this be if we tried to generalize it? Well, that would be that n squared will always divide the nth term of the sequence. So rather than getting caught up in these specifics with 2018, let's see if we can prove the more general statement that n squared will always divide the nth term of the sequence. Certainly, if we can prove that, we will have proven this. Reasonable place to start would be to take a quick look at the first few terms of our sequence to get a good idea of what they look like. And here are the first few terms of our sequence. A1 is defined to be equal to 1. A2 is the sum of the previous terms. In this case, that's just 1 multiplied by the position of A2 in the sequence. So multiplied by 2. That is equal to 2. A3 is the sum of the previous terms. 1 plus 2 multiplied by 3. That's equal to 9. And then A4 again is the sum of the previous terms. 1 plus 2 plus 9, which is equal to 12, multiplied by 4, which is equal to 48. Then we might quickly ask, does our desired result hold for these first few terms in the sequence? Well, 1 squared does indeed divide 1. 3 squared is 9, which does divide 9. 4 squared is 16, which does divide 48. But 2 squared is 4, which doesn't divide 2. So it seems like the result does not work when n equals 2. But maybe if we're optimistic, we suspect it will work for all terms of the sequence afterwards. Sometimes things can be a little bit rocky right at the start of a sequence, so let's be optimistic and hope that we can prove our result for all terms of the sequence where n is greater than 2, so at least 3. I like this problem because things end up working out surprisingly nicely. Firstly, we can see immediately by the definition of the sequence that the nth term will be divisible by n. So the nth term of the sequence we know has at least one copy of n. So in a way, we're already halfway to our result. We just need to be sure that the nth term of the sequence will have at least 2 copies of n. Since we know by its definition that it will have at least one copy of n, we might consider an divided by n. So we can just focus on what remains after we divide out that guaranteed copy of n and see if we can show there is still at least one more copy of n. If you want to try the problem yourself, I would recommend taking that sort of hint and going forth and trying to figure it out. It's pretty straightforward. So let's get into it. We'll take a look at an divided by n. If we divide the nth term of the sequence by n, what's left? Well, by definition, it would be the sum of the previous terms because we divided out that factor of n. So that would be a1 plus a2 and so on all the way up to an minus 1. And remember, as we try to prove this, that we are assuming n is at least 3. Okay, so we know that an over n is equal to a1 plus a2 and so on. If we can show there is a factor of n here, then certainly that will show that an is divisible by n squared. At this stage, we might consider substituting one of these terms in the sum with what we know it must be equal to by the sequence's definition. Then we could get some more multiplication going on if we were to do that. Of course, a1 is just 1, so we might want to focus on the far end of this sum. And let's try replacing an minus 1 with this, which defines it. So the sum of the terms that precede an minus 1 multiplied by n minus 1. So doing that is going to give us this. We're going to have a1 plus a2 and so on all the way up to the term that precedes an minus 1 because we're replacing an minus 1 with an equal expression. So here we've got all of these terms plus an minus 2 plus an minus 1, which we are using the definition of the sequence to replace with this. a1 plus a2 and so on all the way up to the term that precedes an minus 1, which is an minus 2, multiplied by an minus 1's position in the sequence, which of course is n minus 1. Now, perhaps you see something beautiful here. What have we got going on right now? Well, we have a1 plus a2 and so on all the way up to an minus 2. And then we also have another n minus 1 copies of that same sum. In total, what is that? That's n copies of this sum. That's very nice. So what we actually have going on here is one copy of a1 plus blah 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 up to an minus 2 and another n minus 1 copies of a1 plus a2 all the way up to an minus 2. So in total, what we have is a1 plus a2 and so on up to an minus 2 multiplied by 1 plus n minus 1, which of course is n. And there we go. We see we do still have another factor of n even after we divided by the first factor of n. Now, one small detail we might point out is to make sure that these sums make sense. As in, is an minus 2 defined? Yes, it is, because n is at least 3. So these sums definitely make sense to write. And we see we've got this additional factor of n. So then what we might do, since we know that this is equal to this, just to get a little bit closer to what our final conclusion really is, let's multiply both sides of the equation by n. That will give us that an, the nth term of the sequence, when n is at least 3, is equal to a1 plus a2 and so on all the way up to an minus 2 multiplied by n, but then we multiplied both sides of the equation by that n there, so it is indeed an integer multiple of n squared. So by definition of divides, if n is greater than or equal to 3, then the nth term of our sequence will be divisible by n squared. And thus, it immediately follows that the 2018th term of this sequence is divisible by 2018 squared. And that's it.
Subscribe for more of the swankiest math videos on the internet.